This time we're going to look at behavioural Verilog. That means that we can specify using what looks like a programming language the behaviour of the digital circuit. The example I'm going to use is that the input to our chip is going to have 8 bits. So this 7 to 0 signifies that X contains not 1 bit but 8 bits. The order here means that the most significant bit is bit 7 and the least significant bit is bit 0, which is how we normally write binary numbers. We'll worry about that later in the course. Most of the time you just want to do it this way. So if you want to declare a 4-bit number, you'd do it like this. 3 to 0, that means Y contains 4 bits. The most significant bit is Y3 and the least significant bit is Y0. It's important we keep in mind what the largest numbers are that can fit in here. So if it's 8 bits, that means X can go between 0 to 255. Why? 2 to the power of 8 is 256, subtract 1, 255. So in binary, the number 11111111 is 255, and that's the largest number we can fit in X. For Y, the largest number we can fit in it is going to have 4 ones, 1111, and that is going to be 15. The chip that we're making is going to count the number of ones in the binary representation of X. So if X is equal to 0101, 0101, then it's going to have 4 ones in it, and so we want the output to be the decimal number 4. The decimal number 4 in binary is 0100, and so therefore that's exactly how the output Y is going to be represented, by that binary number which humans understand in decimal. Anyway, let's jump in and get started. So we want to count the number of ones in X. I could do this using a truth table, but then I'd have to list 256 entries of my truth table, and that's just too painful to do. There might be other ways of doing this. I'll show you a very simplistic way. I imagine that I want to do this in C code. Now, this does not mean that the FPGA can implement C code or that it runs C code. Not at all. Not on your Nelly. That is not what happens. All that happens is that the synthesis tool Quartus is sufficiently clever, and you do have to give it credit because this isn't easy. It is sufficiently clever to work out how to implement in digital logic the following behavior. So this is not what gets executed on the FPGA. Nothing like that is going to happen. Basically what Quartus does, to put it simply, is it just puts in all 256 values of X, runs the program in here for each one, determines the output, it therefore gets the truth table. In fact, that's probably what it does. So when we specify behavioural Verilog and we want to go and synthesize it, the synthesis tool basically constructs the truth table. Maybe there are some shortcuts, but the way to understand this is that we describe some behaviour, the synthesis tool tries out all the different values of X to compute the truth table for us, and then it goes off and implements that truth table on the FPGA using lookup tables. Okay, let's jump in. Let's try to write this module here. So we need to count the number of ones. The very first thing we do is we need some way of executing some code when something changes. And in this particular case, we want the code to run whenever our input X changes. It's safer and more convenient though to just use star. Both will be the same here. We don't know how many lines of code we're going to have, so we can put in a begin and an end statement here to give us some flexibility. If we think in terms of C, then the way we do this is that we want to count. We want to go through each of the bits in turn and use an if statement to test. Is it a 1? So let's describe that behavior. So initially, y is equal to 0. Because we're inside a begin-end block, these instructions are going to be executed sequentially. So first y is equal to 0. Now I need a for loop. For, and I want a counter. I'm going to call it I and worry about how to declare it in a second. So for I equals to 0, thank you autocorrect, for I equals to 0, I is less than or equal to, I need to go from bit 0 to bit 7. And Verilog does not have plus plus. You have to do I equals I plus 1 for it to work. I can have a begin end here, but I'm only going to have one statement. If xi, so xi is the 8th bit of x. When I is equal to 0, that's x0, that's the least significant bit of x. If xi is equal to 1, now technically I don't have to do this because xi is either 0 or 1 and 0 is false and 1 is true. I could have just done if xi and left it there. If you want your code to be easily understood by everyone, sometimes you consider making it more explicit. That's just a personal coding style. Both are correct. Anyway, if the ith bit is a 1, then we want to add 1 to our count of the number of 1s. And besides having not declared I, that's it. The way this code works, always at star, so the Verilog compiler is smart enough to work out what influences the outcome, what can cause a change. So this star will be replaced by x, because when x changes, then we get a change in y. So whenever x changes, we run this code. Between begin to end, code gets executed sequentially. First we set the output to 0. That's just temporary. That doesn't actually mean the output of the chip is 0 because this code is not being executed. Once we synthesize it, this is going to be digital logic created from the corresponding truth table to what this describes. Anyway, to work out the description, we think we start off with y being 0. Then we go through the 8 bits of the input x, and for each bit that's a 1, we add 1 to y. When we are finished, we have got our final answer for y. So during these calculations, y is changing. These are considered intermediate results to y, not the final value. The final value of y is what we get once we've executed everything. Tangentially, that's why we have got the delay statements in the test benches in the labs. Because variables like y can change as it builds up to the correct value, we don't want to just display y because it might be halfway through these calculations. We need a delay to wait until we've done everything that needs to be done and only then display y. So this code will change y, but it's only the final value that matters, and Quartus will run through all the different values of x, do this calculation here to work out the final value for y. From that, it then knows what the truth table is, and from that truth table, it can then implement this behavior on the FPGA. It does not implement this as a program. It implements this using logic gates based on the truth table that this describes. The only thing remaining is to declare the counter y, and there's a trick here. If I simply do integer I, then it's going to complain that I can't define integers inside a block if the block doesn't have a name. Now this might sound a bit silly, but we can give blocks names. And when you're using Model Sim to debug things, giving different blocks names actually means it's easier to find what you need. Although we won't really do that in this course, we just have to remember if I want to declare a new variable inside my block, then I need to give my block a name. So I have no idea what name to use. I'll call it Fred. To emphasize this, integer I does not exist on the FPGA. This is just part of my code that I use to describe a behavior. At the end of the day, I end up with a truth table, and that truth table gets implemented. Okay, so to check that this works, we need a test bench. Maybe I made a mistake. And by the way, a very common mistake will be to not allow enough bits in the answer Y. So the reason I have got 3 to 0 here is because I ask myself, what is the largest value that Y can be? Well, if X contains all ones, then Y is going to be the number 8. And how many bits do I need to represent the number 8? Well, I need 4 bits, which is why it goes from 3 to 0. If I had put in 2 to 0 here, then if X was all ones, the value of Y you would think is 8, but because you only had 3 bits here, if this was a 2, it would wrap around and Y would actually be equal to 0, and you'd wonder what was going on. So be very careful about working out how many bits you need to store answers. Okay, let's go over to our test bench code now. And for the test bench, the very first thing you normally do is you have a look at the chip that you want to test, you have a look at its inputs and its outputs, and you recreate them in the test bench because you need to wire them up. Now, I'm just going to give them the same names. You don't have to do this. The inputs to the chip you define as registers, almost always, because you want to be able to change them. The exception to this is if you're going to actually wire up chips. If the input to a chip is going to be the output from another chip, then you just use a wire. But I only have one chip here, and I want to be able to control all its inputs, so I need to use a register here so that I can then manipulate the inputs in my initial begin block later. So I need an input to my chip, and I need an output. The output of a chip must be connected to a wire. And you make sure that the number of bits is correct in either case. If you're lucky, you'll get a compiler warning if you get the number of bits wrong, but you won't get an error, and everything will compile, and you'll wonder why things don't work. And it's because you've chopped bits off somewhere without realizing it. Okay, so now I've got my inputs and outputs for my chip. I now instantiate my chip. I go down to Bunnings or JCar and buy one of these little chips. The type of chip is number of ones. I give it a name. I'll just call it N for now. And I wire it up. The fast way is just to match the ordering. The safe way is to say that the input called X is going to be assigned to my register X. And the input called Y is going to be assigned to my wire called Y. Now I've instantiated my chip. It now exists inside my virtual test bench. I need to generate some input signals and then display the output Y. Now I can declare my integer inside the initial block if I name my block, or I can simply declare my integer outside. Integer initial begin, and then there's going to be an end at the end, so I can put it there first. I want to go through every single possible input in order to test that this thing works. So there are several ways of doing it. I'm going to use a for loop again. For I equals 0, I less than or equals to 255, I equals I plus 1. Now maybe it's a bit advanced to point this out right now, but if you prefer, you don't have to use an integer, although it's safer. I could have declared I to be a register, but then I would have had to have made it have enough bits. And it's very tempting to say, because I'm counting from 0 to 255, I should make I a register with 8 bits, because 8 bits would fit 0 to 255. But if I did that, this for loop would never end. And that's because if I is equal to 255, that's okay, this for loop runs. Then you do I equals I plus 1. And I is not going to be equal to 256. It's going to wrap around and be 0 if I had declared I to be an 8-bit register. And because I is 0, it's going to pass this test again, and it will go on forever. So if you do use a register here, you have to make sure that the number of bits can hold not only this number here, but also one bigger. Therefore, it's safer to just use an integer here. Okay, where are we? So I have my for loop here. There are different ways of writing this code. This is not the nicest way of writing it, but it allows me to explain several things as I go along. So x equals I. This simply says that I'm going to make the input to my chip the current value of I. I probably has got 32 bits because that's the default. X has only got 8 bits, so it just truncates from 32 to 8 by chopping off the leading digits. I could, so normally what I do is I then have a delay here and then do a display, but I'm going to do something a little bit different today. I'm going to use strobe. And what strobe does is it says, don't print out the answer right now, wait until we've got the final answer and only then print it out. And why is that important? That's important because over here, the value of y is going to be changing. What happens is when I do x equals to I in this module and everything's in parallel, remember that the simulator and the hardware, everything's running in parallel. So as soon as x gets changed here, this always thing's going to be triggered. Over here, this always, as soon as you have an always statement, it means you grab a friend and your friend looks to see if there's a change to the parameter here. We already discussed that this star represents x, so as soon as x changes, this is going to be run. So when x equals to I occurs, x changes, so one friend is going to be running this, and another friend is going to start running this code. And this code here, y is going to change. Y is first going to be 0, then it might equal a 1, and then maybe a 2, etc. Y is changing. If I did a display here, without any delay, who knows what value of y will I get? I might get the old value of y. I might get the value of y straight after this y equals to 0. I could get one of these intermediate y's, or if I'm very lucky, I might actually get the final y. Because this and this are running in parallel, you have a race condition. You don't know which one's going to do what first. The strobe says wait until you've finished all calculations at this current time step. And we'll discuss time steps later. But it says wait until everything's finished and then print out the answer. So it's safe to use this without a delay. The strobe is just like a display statement, and I'll show you another new trick. We can have C-like formatting in our strings. So %8b means that I'm going to pass to it a variable and I want it displayed using 8 bits in binary. So that will display the value of whatever I pass to it in binary as opposed to decimal, and it will use 8 characters to do that. So 8b has $1. 1D, 1s, and I pass to it X and Y. So this will print out, so if X is equal to 0, it should print out 8 zeros, has a single 0, 1s. You can go to tutorials point, find a Verilog online compiler, just Google tutorials point has one, and you can type in this code and you can run it, okay, once we're finished, and you can check that everything works, and you can then see what each statement does. Okay, now we have to have a delay in here because we're talking about digital hardware. If there's no delay, it's going to run through, I is going to run from 0 to 255 at the same time instant, and only when it's finished will the strobe trigger. So we have to tell it we've finished at the current time step, and so we need a delay there to move on to the next unit of time. And a #1 on its own is not a statement. I need a statement following it, but there's nothing else I want to do, so I put a semicolon there. And now our code is done. A simpler and very powerful behavioural Verilog description, and ignore the capital letters here, is to do arithmetic. So if I have got, say, my complicated calculation input, and I can have an 8-bit number X, and my output might be a 16-bit number Y, and I can simply do assign Y equals X times X, for example, to compute the square of X. Again, Quartus is going to go through this and compute some sort of, in principle, it's got a faster way, okay, but in principle it will go through this, compute the truth table for this mathematical function, and then implement it on the FPGA using combinational logic. So we're free to use any arithmetic we want here, multiplication, addition, subtraction, etc., etc. We do need to worry about signed numbers at some stage, but that will be later in the course. So being able to do arithmetic means it's very convenient to implement digital signal processing algorithms on the FPGA, because Quartus can understand mathematical operations, and by implicitly computing the truth table, it can figure out how to implement them on the FPGA.